Eigenvalues and Eigen Functions. We have obtained the steady state Schrodinger equation E psi equal to minus h cross square by 2m del square psi plus v psi. Or E psi equal to h psi, where h is the Hamiltonian operator minus h cross square by 2m del square plus v. We have seen that in quantum mechanics all dynamical variables are associated with operators. When these operators operate on the wave function, we get the corresponding value. The momentum operator is P equal to minus IH cross di by dx, and another energy operator is E equal to IH cross di by dt. So we have the steady state Schrodinger equation E psi equal to h psi. When we solve this equation, we get large number of wave functions psi n, and correspondingly there are large number of energy values En. So we can write the equation in general as shown in this. H psi n equal to En psi n, the Hamiltonian operator operating on the nth wave function or wave function of the nth state. We get energy of the nth state into wave function of the nth state. H operating on psi n gives En psi n. For example, we know that the first orbital, 1s orbital of hydrogen atom has a particular wave function. When Hamiltonian operator operating on that wave function, we will get the energy of first orbit, E1. When Hamiltonian operator operates on the wave function of 2s orbital, we get the energy of the second orbit, E2. When the Hamiltonian operator operates on the wave function of third orbital, 3s or 3p, we get the energy of the third orbit of hydrogen atom, E3, and so on. So when we solve the Schrodinger equation time independent form, we get different values for energy, and corresponding to energy, each energy we will get different values for the wave function. Why we use the time independent form of Schrodinger equation or steady state form? Because in almost all systems the potential does not depend on time explicitly. Potential energy or energy of the system will not change due to time alone. The potential energy does not depend on time explicitly. It has implicit dependence. For example, in the case of hydrogen atom, the first orbit has a particular potential energy. Second orbit has a particular potential energy. The potential energy of an electron in first orbit will not change with time. Will not change with the time only. It will change when it changes the position from one orbit to another. But it will not change as a result of time only. So, the potential of many systems have no explicit dependence on time. So, we need not use the time dependent form, because the time independent form or steady state form is more simple. So, we have eliminated the time dependence and derived the time independent form or steady state form. And that is this, H psi n equal to En psi n. And this equation gives the energy values and corresponding energy functions. When we solve the time independent Schrodinger equation, we get exact solutions only for certain discrete values of energy, and that energy values are known as energy eigenvalues, and corresponding functions are known as energy eigenfunctions. So when we solve this equation, this time independent Schrodinger equation, we get different wave functions corresponding to different values of energy. And these wave functions are known as eigenfunctions, and the energy values are known as eigenvalues. Specifically, energy eigenvalues. Eigen is a German word meaning proper or characteristic. So eigenvalue means characteristic value. Eigenfunction means characteristic function. This is the reason why H psi n equal to En psi n is called eigenvalue equation, energy eigenvalue equation. Not that H is an operator. It is known as Hamiltonian operator. So H operator satisfies, or H operator has an eigenvalue equation. Similarly, we can think that every operator associated with physical quantities may have an eigenvalue equation. So every physically meaningful operator has an eigenfunction and corresponding eigenvalues. Corresponding to position operator, momentum operator, potential energy operator, kinetic energy operator, total energy operator, Hamiltonian operator, we can write an eigenvalue equation. They all have eigenvalues and corresponding eigenfunctions. The momentum operator operating on wave function will give the momentum eigenvalue and momentum eigenfunction. So H, in this energy eigenvalue equation, H is an operator and En is an energy value. It is a scalar quantity. And the psi is the eigenfunction, which is a mathematical function. So generally, for every operator, we can construct or we can have an eigenvalue equation. So general eigenvalue equation for an operator A can be written like this. Operator A operating on the wave function psi k gives a scalar quantity lambda k into the same wave function psi k. represent the order of the state. So an operator operating on the wave function gives the same wave function multiplied by a scalar quantity. Then this wave function is known as Eigen function or eigenvalue function, and the scalar quantity is known as the corresponding eigenvalue. So that is the definition of eigenvalue and eigenfunction. If an operator operating on a wave function gives the same wave function with a multiplicative scalar quantity, then the wave function is known as eigenvalue function or simply eigenfunction of the operator A, and the corresponding scalar quantity obtained lambda k is known as the corresponding eigenvalue. So eigenvalues are the possible values of measurements of an operator for which the Schrödinger time independent equation can be solved exactly. So this is a new concept or an important concept in quantum mechanics. Eigenvalues and eigenfunctions. So we have steady state Schrödinger equation. When we try to solve them, we can solve them exactly only for certain discrete values of energy. And that values are known as energy eigenvalues. Corresponding to that values, we will get some functions. They are energy eigenfunctions. So this equation, steady state Schrödinger equation, is known as energy eigenvalue equation. It is an eigenvalue equation valid for energy operator or Hamiltonian operator. Similarly, for every physical quantity we have an operator, and for every operator we can have an eigenvalue equation like this. If the momentum operator operates on a wave function gives the same wave function with a multiplied by a constant, then the wave function is the eigenfunction of momentum operator, and the corresponding scalar quantity or multiplicative quantity is the eigenvalue of the operator on this wave function, eigenvalue of momentum operator. Generally, if an operator operating on the wave function gives the same wave function with a multiplicative scalar quantity, then the wave function is known as the eigenfunction of the operator, and the scalar quantity is the corresponding eigenvalue. So eigenvalues are the possible values of measurements of an operator. This is the eigenvalue, general eigenvalue equation. A psi k equal to lambda k psi k. Thank you.